Hi there, welcome back. So we continue our work on this time on the four member ring. We worked, we pop, we displayed the work on the three member ring, the chemistry. And the biochemistry. Okay, so now we are going to talk about the four member ring, okay, such as when X equal oxygen, it's oxytane. I hope you are very fine. Everything fine. Protect yourself, okay? Take care of your family. Keep going. One is NH and R. Its name acetidine. Cyantane. Oxytane, acetidine, cyantane when it's sulfide. When it's nitrogen, acetidine. When it's oxygen, it's oxytane. So let's start with the oxytane. For one, synthesis. Just one thing, free member ring stability are more stable than a four member ring. One more thing, when you have an heteroatom X, you always start in the with the heteroatom 1, 2, 3. So if this is a heteroatom, it's delta minus because the electron density is high. Then you continue to the next, if there is a neighbor here. Okay, let's 4, 5, no matter. So here T is delta minus, delta plus, delta minus, delta plus. Okay? 1, 2. So for example, you have an epoxide with a double bond. So you have here delta minus, delta plus. It's the electron density. Okay? Delta minus, delta plus. It means delta plus. It means if you have a nucleophile, it could attack at this position, this one, and that one. Okay, so this scheme, you have to do it every time to find the position of reactivity okay, always do like this. Start with the heteroatom. The heteroatom is the one with the high electron density. then the neighbor alternate between minus delta, delta plus, minus, like this. Okay? So you know the reactivity, you know which position is where you can have here an electrophile, here an electrophile. So it depends on the electrophile, okay, the position. And here you can have an electrophile, or here. So depending of if it's soft, I'll give you a clear example. For example, I take back my epoxide reactivity. This is very important. If you understand that, you understand the logic of organic chemistry. If you have an epoxide, 1, okay, delta, that what we said, it minus, okay, minus delta. Let's go here, 2, 3, okay, 3. So delta plus because it's nearby an electron. So this one is delta minus, this one is delta plus, okay? That's very, very important. 4 and 5. Okay? So you can add an electrophile at the position 1 and position 4, okay? Because it's electron rich. Okay? So the nucleophile could attack at position 2, 3, or 5, okay? So addition. That's very, very important. This is a very simple rule that explains your reactivity in organic chemistry. Okay? So, if you want to attack at position 5, you need a soft nucleophile. You need to employ a soft nucleophile. If you want to attack at position 2, position 3 is more important than position 2 because this one you have bulky group, and the bulky group is that one. Okay, because it has a clash with the Donitz angle. Okay, that's very important. Please keep that in mind. This is a simple rule, but if you keep like this, and it's even the same when you do the retrosynthesis, always think like this. This simple rule help you to know at which position you should cut and you should add. So you can find the best bond. Okay? So you can find which bond, which position you can where you can do reaction. When you have no clue how reaction work, you just do that. Every time you start with that, okay? Always start with that. So you understand which position can react and which one cannot, okay? And for position 3, you need to use like hard nucleophile. Okay, so like soft nucleophile is like sulfide, nitrogen, some like oxygen, okay, even smaller, small. Hard, it means small, less electron, hard. Soft, a lot, I mean more electron, comparing to hard, more electron, okay. All right, so for the synthesis of 3 1 1 synthesis of oxetane, you can employ sorry. With halogeno-chlorine in water, 100 degree, at least 1 equal, I mean, you can control. Anyway, the number of recurrent is not important because this reaction is fast. It's the most thermodynamically favorable reaction. Okay? You can acetylate. I think if you protect, for example, I don't think tritilamine, 1 equivalent. You can use an OH, but here is the same reaction, okay? It's the same, just you cleave this position, then you release an O-. One thing, again, intermolecular reaction, intramolecular reaction, are more favorable than intermolecular reaction. Why? Thermodynamically is more favorable, okay, than like a polymerization polymer. So if you want to get the intramolecular product, increase the temperature, okay, and also dilute the solution. And for the other addition, had the base later, had the base dropwise. If you want the polymer, reduce the temperature to get the kinetically, because this is a kinetic product. I mean, in this situation, okay. This reaction is the most favorable, like 2 1 2 1, okay, so it's faster too. I'm wondering if it's the polymer is more stable. Yes. No. It is more stable. Yeah, because it's just one. And here is a lot of entropy, a lot of disorder. So increase the concentration. Add dropwise. No, together, sorry. Everything together. In one shot. High concentration, decrease the temperature, so you have more chance to get the polymer. So, all right, I hope it's clear. Second way, oxytane by activation. So you can take the bis alcohol, so you can activate it with tosylate, okay, OTS. S chlorine with the base. You can use this base, okay, or butyllithium, one equivalent in THF, always minus 78 degrees. 2, add this reagent. Okay, so now you can guess what to do if you had like one equivalent of a base. Okay, they use here butyllithium, so the protonates intramolecular cyclization. Okay, to get this product, oxytane plus the tosylate lithium, 4, 1, 3. Photocyclization. Using this ketone phenyl plus double bond. So by using light, okay, so you can get UV light, so what happened, the double bond by become pi star, okay, maybe I should say that, sorry, it's more the pi of this carbonyl it excitated to pi star, and the pi star interact the pi orbital interact with the pi star of the carbonyl to give the product. So two type of product, okay, you have 1, 2, 3, 4, or addition 1, 3, 2, 4, or 1, 4, 3, 2. So you have two couples of product. You have this one, phenyl, point, star, this one, intramolecular cyclization of this double bond. Oops. So you understand the principle. But there's one product that is dominative. Which one? This one? Product A or product B? I give you two minutes. Always think about when you do the reactivity, kinetic, the stability of the intermediate, okay? This is the intermediate. Which one is the highest? This one, A prime or B prime? Then you can see which, why is A, why is B in terms of energy. Always think about in terms of energy. I give you 2 minutes. Okay, you got it. The most stable product is obviously A. Maybe 90%, more or less 10%. Okay, so the reason is simply because one rule: when you have a carbocation, stability of carbocation is as follows. For radical is the same. So you need one air increase, number of air increase on C1, on C1. What happened? The stability increase. And one thing, you have more, you can have even more hyper conjugation. Okay, so when you have, when you have a radical, when you have an anion, It's opposite. Carbanion. So when you have double bond like this, when you have less, when air increase, stability increase. Because so H is more stable than air. Okay. Okay. This is how it works. Okay. Then for the radical, this is very important rules. Radical, when air increase, more stability. Especially if conjugation. Stability increase. Okay. So that means it means that for air, point here, air is more stable than air okay. Sorry, this one is the same. Yeah, you guess 2H extra 1 then CH3. So we come back. So this is why A is more stable than B, because you have more air, more stabilization, more inductive donor than here. Okay, you have only one carbon giving. Here you have 3, so this one is more stable. It's lower energy. The energy barrier EB EA is lower than EB, so Ka is higher than Kb. Okay, Boltzmann constant. All right, I hope you are enjoying it, because this is very simple rules, but very, very important to understanding. For the understanding, deep understanding of the chemical reactivity. Organic chemistry, very simple, as long as you have all these simple rules. And the thing about logic plus simple rule and these 3, you can do all compounds. All your compounds that you can imagine. Another example, interesting example. Photochemistry is currently a hot topic. In in organic chemistry, not only heterocyclic chemistry, but in methodology. Many people use it. Macmillan, David, Professor David Macmillan. He's expert of photochemistry and organocatalysis. All right, so let's continue. Okay, I can give you another example. So 18. You can get no matter if R are the same, and the other diastereoisomer, diastereoisomer. Oxetane, synthesis of oxetane, 2 ons. It's just like this is this product, oxetane and 2 ons. Oxetane, 2 ons. Forgive me for the writing, it's because again I just explained I broke my hand several years ago, and I stopped doing sport, practicing sport because of that. So typically, to make this compound, this is the classical methodology used broadly if you want to do an esterification. They use tosylate. Okay, tosylate, I'll remind you. Pyridine. Typically, first step, you activate this position. It's a good question. Do you activate this position first or this one? The most reactive is this position, so you form O tosylate, O minus, then you attack. Because this one is more reactive than this one. What about this one? What about you form? You deprotonate this one is then pyridine addition, pyridine, remove it. I have to say which one. I think this one. I think it's more near this one. Anyway, this is a product. You can I can check which one is the best, if it's true what I'm saying. Okay, good work. So ketone plus ketane okay. 1 4 1 2 sorry 4 2 thietane. So you take there are many ways to make it. There are two main ways from the same reaction, from the chloro, I mean any it could be chloro, chlorine, bromine, iodine. So you need a base. So you deprotonate NaOH, NaOH, KOH. Yeah, I have one question. Which base is the best between cesium? Na plus. One thing about physics, if you have when it is bigger, K plus, it's a very nice rule that you should know. RK plus, RNA plus, R cesium plus. So the force is proportional to the is proportional to the distance between the two atoms. Okay, so that means when it is bigger, is proportional to the radius of R minus multiply R metal. Okay, R minus R in that case. Okay, that means if the radius is bigger, the force is lower. Okay, it means that for O minus cesium, distance is bigger, there's less force. Sorry, minus K plus Na plus. Okay, this is how it is. All right. So reactivity increase, more reactive. because more available. All right. Let's have a 5-minute break, okay? Then I will be back. Then we finish the first 100 page of this René Milcent book, and we'll finish this month hopefully 600, the missing 600 pages. So very advanced heterocyclic chemistry with all the thinking process, okay, plus thinking process plus some projects. So where are the unique people doing that on YouTube? So keep in touch just after. Just see you. 5 minutes, 10 minutes. Okay. So let's I hope you enjoy this format. Anyway, all right. I hope you're enjoying this format, and the aim is to explain you in detail the reactivity of organic chemistry. It's very simple if you use if you know how to play with many steps. Okay. So we are working on styrene. Page. So I just remind you, this is a book from 2003, and I just expand it as much as I can. Oops. Just have a problem with my pen. Sorry for that. I need to. It's not writing well. Sorry, I have some small issues for writing. Okay, got it. Yeah, it's repeat. So we talk about the preparation. Okay. So you can even prepare them with bromine. Bond NH. So you can imagine an attack like this on the two position. First, it's an attack with the. So they use chlorobromine to facilitate first the attack of the sulfide. So I understand. The base, no base, no need, because you protonate this. Protonate this position. This is the product. Okay, then yeah, you can have the base. You need to have the base. NaOH. So to deprotonate this position, you can guess what will happen. So what happened? NaOH. Remember, when you don't know when it can react, you start. Okay, let's start with sulfide. No matter. Delta minus, delta plus. This one is delta plus. Delta minus, delta plus, delta plus, delta minus. Okay. So if you have an NaOH, what can an NaOH can do? It can attack this position, this one, or do the acido-basic elimination. I mean substitution, proton substitution. In that case, and now attack this position, because this one is more reactive than this one. Okay, because you have a delta plus, more reactive. And if you deprotonate, it's an equilibrium. Sorry, NH3 plus, 2 plus. It's an equilibrium. NH2. Okay, so if you had an NaOH, I know it can come back. Okay, it can come back, but it's not. It's quite slower. The difference is not so big, so it's not so fast. So the attack is most favorable. So you have addition, elimination. Okay, so you have your product. Plus, so the reaction is, exact reaction is this is the mechanism. Okay, results. So I just remind you that I'm writing a book. I'm writing a book about supramolecular chemistry, okay? If you want, next year I will, 800, 900 pages. Next year, if you want, I can make one on heterocyclic chemistry, okay? Very formal. Here, this course is not formal, but it just, because it demands a lot of work. I'm preparing this book. I'm preparing this book and I'm adding a lot of details. That's why I'm spending a lot of time making PPT. Sorry, I cannot make the PPT this time. Okay. So, acetidine. Is the same. It's always the same. The simplest reaction is to take this one, base, and you have electron class cyclization. There is another way. Which is quite a bit not so broadly used, but if you have methoxylate, the base, you deprotonate and it attacks this position. With this reaction, you can make a macrocycle. I mean, all the reaction in organic chemistry, you can take the list. You can have whatever you want as heterocycle. You can take whatever you want as a reactivity, and you can cyclize, or make like this or like this, or intramolecular, or with 2 or more. So enjoy all the chemical reaction to make the macrocycle or the polymer that you want. Here is a small cycle. We use sodium isopropanol, it form and it cuts the bond and you get acetidine. a way to get beta lactam. Is to use this top. Cyclization before. This product, which is quite really then you can cleave it. SS plus pyridine to cleave. But be careful, you should be careful had one equivalent, because otherwise you have, so okay. Otherwise remember, so you can cleave here delta plus. This is a delta plus. This one is delta plus, delta minus, delta plus, delta minus, delta minus, delta minus. Here the sulfide is there because it's conjugated. Delta minus, delta plus, delta minus, delta plus. So if this one can attack this position, okay. So be careful. I mean, if you have to do this reaction, so the product is R2 R1. Again, I'm sorry for my drawing style because my hand are broken normally. I would be pleased if you need for free. I can draw you. If any question about that, I can draw you with Kendall. So ketene. So you can use with by heating. Okay, so for free chemical properties of these beautiful compounds. They are very important compounds for this cycle, are very important for as antibiotic. Okay, so this is mine meaning properties of, so I said which one, 3 4 3 1 oxetane. So with HCl, what will happen? Remember, you have here this one, and you have an electrophile. So this one react delta minus, right, with electrophile. That's why by keeping this this style of representation, you have big chance to make it very simple. Then you have the chlorine. Where chlorine can attack. So you have a delta plus. So electrophile. So you activate this position. So it can attack here or here. So why it attack? It attack at the least substituted, remember? Donis angle. Let's check. I will tell you what, I think it's around 40. Let me check. Donis angle. Sorry, it's not Donis, it's units angle. Units angle. So it depends. So comparing to from here, angle is 107. There is also the flipping lodge angle, but Donis angle is the most. That means if you have a substituent at this position, you have more clash. Okay, imagine. But here is depends. Yeah, I will present it more in more detail next time. Depends what you use. Okay. All right. So the attack, so we come back. So the attack occur at the least substituted, okay? That means tac, 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 OH. Yeah, okay. This one is substituted. But be careful, if R equals CH2, CH2, okay? But be careful, very, very careful. It's, if you have that, it's different. H. Here is different. Here you open when you have conjugated. If you open, if you open, the carbocation is more stable here. It's different because here you open first. Okay, and it's conjugated. That means you have a double bond. Then the chlorine attack. Okay, this is the main product. Be careful, think about of the carbocation versus then its angle attack, so less substituted position. Okay. So if you had an acyl chloride, is the same, so it will attack at this position. mainly. A little less here, less. So that means okay. Yeah. If it's CH3, careful, the ester are not quadrate with some the tension of this product is high, so they are not so stable, so they want to open quickly, as quick as possible. And when you have a CH3 here, so you can guess where it attack. Okay, yes, you are right, it attack from here, one, so it attack here, the chloro attack here, acylation. So we have 1, 3, 1, CH3, oh, acetate. Okay, so let's continue the course today or tomorrow. Okay, I hope you have enjoyed it, and see you soon. Okay.